This will be the third and final video on analysis of variance. Please make sure you've gone and watched the first two videos. If you haven't done so yet, this video will not make sense to you, so watch the first two ANOVA videos before you've watched this one. So in the event that we reject the null hypothesis for ANOVA and that the means are not equal to one another, we've got a variety of different alternative hypotheses which may be true. And ANOVA doesn't initially indicate to us which of these alternative hypotheses are most appropriate. Now we can use multiple comparisons, which we're going to be discussing in this particular lecture, in order to determine which of those means are different from one another. Now the key is that the null hypothesis needs to be rejected before we can follow this step. So you cannot do multiple comparisons if the null hypothesis is not rejected. So this is a key. So let's go to our example from our fish in our different Bayes systems. Based on our ANOVA, we found that the F value was greater than our critical value, so we can reject our null hypothesis because we have a significant P value. So there's a statistical difference in the size of these fish. But then the question is, well, which Bayes are different from the others? So we can use the least significant difference in order to determine which of those Bayes is different from one another using pairwise comparisons. Again, this is only if ANOVA is significant. If we don't reject the null hypothesis for ANOVA, we wouldn't take this next step. So the least significant difference is the smallest difference between two of the means that we're comparing that indicate that they're statistically different, meaning that those groups are different. And this method approaches it as if we are treating these two means as if they'd been the only ones that had been compared. So any difference between these two groups that's equal to or larger than the least significant difference suggests and indicates to us that they're statistically different. So in our particular case, we have our three different Bayes, and we know that there's at least one group that's different than the others. So now our trick is to find out which groups are different from each other statistically. And we're going to use both our raw data as well as our ANOVA table to do this. And so again, the first step will be to make sure that we have a significant difference between at least one of our groups using ANOVA. And then we're going to use the following formula here, in which our least significant difference is going to equal Q times the square root of the mean sum of squares within groups divided by sample size. So these first two components here on the left are things that we're familiar with. So the mean sum of squares within groups, that's going to come from our ANOVA table, and the group sample size is going to come from our data. Now this Q value is a little bit different. So we can go ahead and we can fill in that aspect of the formula, but we're going to need to use a different table in which to determine what this Q value is. And this is our studentized T value. So we can use the following table in which to find that Q value. And here we're going to use the number of groups and the error degree of freedom in which to do so. So these values in the interior of the table are those Q values, and this is what we're after. Now the area in red here, the number of groups, this is relatively easy for us to discern because this is just the number of different groups that we have in our test. In our case, we have three different Bayes, so that would be the number of groups. Now this error degree of freedom is something new. But if you've been doing the reading in the book, you know that there's synonymous terms of this within groups and the error. So the sum of squares within groups is synonymous to the sum of squares of the error. We're going to be using this sum of squares of error moving forward, so this is a good time to become familiar with it. And the sum of squares of error refers to, again, this portion of the variance when we're doing the ANOVA. So the degrees of freedom of the error are equivalent to the degrees of freedom within groups. So we can take this information that we have, and we can find where these values intersect, just like if we were doing an f-test, a t-test, or an ANOVA, or a chi-square test. We then find our q value, which is 3.77 in this particular example. We can then take that q value and put it into our formula, and we get our least significant difference. So this is the minimum difference between the means of our groups that would indicate that they're statistically different from one another. Again, ANOVA is telling us that at least one of those groups is different, but it's not telling us which group is different. So now we're going to take our data with this new information, and we can then discern which of those groups are different. So the first step is going to be to take the mean of our respective data. And then we need to calculate the difference between these means. So we need to take the difference in the means of the Galveston Bay and the Matagorda Bay fish. We need to take the difference between the Galveston Bay and Corpus Christi fish, and the Matagorda and the Corpus fish. And then we need to compare these to the least significant difference. And anything that is less than this least significant difference will not be different from one another statistically. The only difference that we observe here is the fish between Galveston Bay and Corpus Christi, and that the difference in the means is 13.8 centimeters, and our least significant difference, meaning that minimum threshold that we need to exceed, is 11.698. So it does indeed exceed that threshold, so we can say statistically that the fish in Galveston Bay are different from the fish in Corpus Christi Bay. So if we were to represent this visually, say on a box and whisker plot, we would plot our data, and we've got our mean, our median, our quartiles, and our whiskers, and we would indicate that Galveston Bay is one particular group statistically. We can indicate this by A, and we know that it's different from Corpus Christi in the size of the fish, and so we would indicate that Corpus Christi is a different group statistically. Now, Matagorda Bay is not different from Galveston Bay or Corpus Christi Bay, so we'd label this with both A and B, indicating to the viewer that Galveston Bay is different from Corpus Christi Bay, but Matagorda Bay is not different from either of these two. Now, we went through this example pretty quickly, but we'll be doing so in class more, and I'd also encourage you to check out section 11.3.2 of your book. So we're at the end of the road for ANOVA, and we're going to move forward after this lecture. But some important things that you should know is when you should be using ANOVA and why we're not using multiple t-tests, extra calculations, increased likelihood of rejecting the null hypothesis when it's 2, type 1 error. You should know how to calculate the total sum of squares among group sum of squares and within group sum of squares if you're given the other two, and how to determine the degrees of freedom for each of these, and then how to calculate the f value based on the mean sum of squares and determine if the null hypothesis should be rejected. And then lastly, as we covered in this video, how to determine which means are significantly different from one another based on the least significant difference if we have significant difference in these means based on ANOVA. So moving forward, we're going to start talking about correlation, and we're going to move from data that are in particular categories to continuous numerical variables that are compared to one another.